So I'm also thankful to be here again. I come back, I'm always so inspired by the power of the team effort and the organized team effort and the sophistication of the big data. So thank you. And I take the opportunity, those 5 minutes, to talk about one more story on a functional role of active dendrites. And the story is about noise. So our brains are made with small molecules. Our brains process information with molecules so small they're incredibly unreliable. And so I wonder sometimes if there's another way for neurons then to pack up tons of those unreliable devices and use that noise to some effect. And in physics and engineering, it's known that noise can have a beneficial effect. There's a phenomenon called stochastic resonance. If you have an array of binary detectors and you add noise, as you see on top, the image quality can increase. This would correspond to neurons in a subthreshold, generally subthreshold regime. However, if you're using, instead of binary detectors, you're using a digital transducer, noise would generally just degrade the image. And that will correspond to neurons, again, in a generally suprathreshold regime. So how can neurons use noise? So I was interested in that setup where you have sodium and potassium ion channels distributed on a soma and dendrite. And you have more ion channels in the soma, in the cell body, which means that the soma is much more deterministic. It has a short classical refractory period. In the dendrite, it also can generate action potential with sodium and potassium ion channels, but in a smaller density, which means there's more finite size effects, more finite size noise, and this compartment is slightly more noisy. It has also a longer refractory period. And so an interesting property that arises is that here I simulate this single neuron, and I give it a weak input. It's very simple. And you see that in the blue trace, you have a soma that doesn't reach threshold until the red trace, this is the membrane potential of the dendrite. It's much noisier, has more intrinsic variability, and it can reach threshold due to that intrinsic variability. And this spike then creates a spike in the soma. And the other scenario, where you have a stronger input in both cases, the soma is firing due to the input, but the dendrite is not eliciting the spikes because of its longer refractory period, so it's quenched. So you have this interesting picture that could be potentially very useful, where on weak inputs, this noisy unit is driving the responses. And for stronger inputs, the more deterministic unit is driving the responses. So to look at this in another way, you can look at the firing rate response of a cell body that's more deterministic in blue, and if you add more noise to that same compartment, you're stretching the dynamic range. But a cost of this increase in dynamic range is that the noise also introduces variability, as you see on the right. So the variability of the red line, which is for the noisier compartment, is higher than the blue line. If you connect those two compartments, the firing rate shows, again, a larger dynamic range, but the variability keeps to the lowest of the two curves, the two possibilities. And so I asked the question of whether this setup can increase the information. So in a simulation where I have an array of neurons that are either deterministic or I tweak the amount of noise in the red units, and I inject time-dependent input, and I characterize the Shannon information. And I want to know whether adding noise to the units can actually increase the amount of information. So that's what I see with those noise, the small compartment, the red compartments here, whereas I increase the amount of noise, I have a small increase of a certain increase in the information, but only for a small range of noise. If I increase the noise in this dendritic compartment with coupling with the soma, as I was showing earlier, then the information is increased, but for a large amount of noise and for larger levels of noise. So with this, I conclude that noise can help to increase the amount of information communicated by cells, particularly with dendrosomatic interactions.